In this video, we're going to go over a binary tree Java code example. So here we have a code for a tree, and we're going to go over what is this tree and what is the stack. So a stack is not numbers. It's not a stack of numbers. It's a stack of subtrees. Stack of subtrees. So each item in the stack is a node that may or may not have children attached. So each item, it's gonna be a node and it's gonna have children, or it's gonna be a leaf. No children. So for example, it might be like a single node that's 5. It can also have a subtree that is 2 times 8. And then it can also have a bigger subtree that is going to be 5 plus 2 times 8 as a tree. So when you have a node, our most simple thing that you have would be something like this. You have class, node, you have string, value, you have node left, you have node right, you have node string value. This dot value is equal to value and closing. So one node, it can be a number, and the number will always be a leaf. And if it has children, that means that it's an operator. So that means that if it's an operator, it's going to be an internal node. It's not going to be one of those ones that are on the very bottom. And it's like connecting other ones. If it's an operator, it has left and right children. So let's see our code here. Stack node is equal to new stack. What this does, it's going to create a stack that holds node objects. And those objects are going to be trees, those subtrees. Now, after this, we see for string token postfix. What this means is that we are going to go through, it goes through the postfix expression one token at a time. Token at a time. So for example, you would have like postfix 528 times plus 3 minus. Now, we have different cases. So this is case 1. Case 1. If is operand token. So here what we see here is node operand node is equal to new node token. Stack.push operand node. So what this is going to do is saying that if this token is a number, it's going to create a new tree. A new tree node. And then it's going to take that new tree node and then it's going to push it onto the stack. But this node has no children yet. Now, let's move on to our case 2, which is going to be down here, or else, case 2. So, if our token is an operator, we're going to pop the top element of the stack. This is the right subtree. It was pushed most recently. It was using our LIFO behavior. Stack is LIFO. So, the reason this is important is because postfix works like this. You have 5 to 8 times. And then when you're at your times, your stack right now is going to be 5 to 8, right? And then the last thing that was pushed, that was the last thing that was pushed. 8 is going to equal to your right operand. The one that's before that, this is going to be your left operand. And because our stack is LIFO, so that means that your pop is going to give you your right, and then your second pop is going to give you your left. So then here you have your node operator, new node token, and then you have operator dot left is left, operator dot right is right. So now after that, we're going to build a new subtree. So your subtree is, for example, your left, if your left is equal to 2, and your right is equal to 8, and your operator is equal to times, it's times to 8. Then after this, you have stack.push operator. So now let's do a full simulation of like what this would look like now that we see our code. So you have 5 to 8 times plus 3 minus. First, you have 5. So when you have 5, you're going to have push node 5. So your stack is going to look like this. Stack. Your 5 is going to push, and then it's going to be there. Then after this, you have 2. You're going to push 2. Then you have 8. No, you have 8. You have push 8. Now, after this, you have your times. This is going to be a multiplication, so you're going to pop twice from your stack. So you're going to pop off 8 and 2. 8 is your right because it's first. Then second is your left because it's that. Then you are going to do a building of this. You're going to have times, and you're going to have 2, which is your left, and then you're going to have 8, which is your right. And then you can push this whole entire thing. You're going to push your expression 5, you're going to push your expression 2 times 8 onto the stack. So now you have on your stack 5, which is below it, and then you have 2 times 8. Now after this, you have your plus. But let's build our full tree. As of right now, it looks like this. Plus 5 times, and then here you have 2, 8. Now we're pushing it. And this is when you do your plus. So you have your plus, and now you're going to have to push this whole entire thing onto the stack. So this, as an expression, this is going to be your pop twice of that and your 5. That is plus. And then you're going to push that. I'm just going to use this. Push 5 plus 2 times 8. And you're going to have this. So that's currently what's on your stack. 5 plus 2 times 8. Now, after this, let's do our next expression. So our next thing is going to be our 3. So you're going to push your 3. 3 is going to go right there. After this, we're going to have your minus. Now your minus is an operator, so you're going to pop twice. 3 is right. This is left. So now if you build your final tree, it's going to be minus plus 3, 5 times 2, 8. And then you're going to push it. So let's push it. Push your full tree onto your stack. And what you could have done instead of writing these in parentheses like that, like I wanted to show you how things were how we eventually end up with our full evaluation of our expression on the stack. But if you just evaluate it using math, or like as you go by step, like 2 times 8 is 16. And then here you have 5 plus 2 times 8. There's actually should be like a parentheses right in between that. Hold on, let me add that. You have 2 times 8, 16. You have 16 plus 5, so that's 21. And then here in the bottom, you have this. 3, pop twice, your subtraction, and then you would just do that. But instead, we just wrote the entire thing here. So you would push that full tree expression, which means you would just push this whole thing. So that full tree expression would just be what we had up here. It would just be the expression. Do we write it here? Yeah, it would just be that full expression onto the stack right here. That would be your 5 plus times your 2 times your 8 minus your 3. So then this whole entire thing would be on the stack right here. Minus, that was minus 3. So that whole thing would be on the stack. So in the end, whenever you have finished evaluating, there should always be one value. That's the reason why there's one value, is because everything has been evaluated. It's one expression. There's just one thing that your whole entire mathematical expression, it should just boil down to one single value. That tree is going to be the root of the entire expression tree. Root of your entire expression tree. Entire expression tree. So we pop it and return it. Postfix is always going to make sure that we have your operands. So postfix means your operands come before your operator. So when you see an operator, you need to require subtree. It requires 2 subtrees that are already waiting on the stack. Your stack is not holding numbers. It's holding these mini expression trees like we saw here. All these mini expression trees. So every time we saw an operator, like here, we saw an operator here, and we saw one here, and we saw one here, that means that you saw 2 mini trees, and you're going to combine them into a bigger tree. And then eventually you're going to take that big tree, and then you're going to pop it back onto the stack until one giant tree remains. You've got your giant tree. So yeah,